Okay, so in the previous video, which covered the Veritasium video, which questioned the speed of light being constant in all directions, as I was preparing for that, as I often do, I'll throw everything on a whiteboard and see what I got, see what I'm going to keep, see what I'm going to throw out. But in the course of kind of doing a workup for that previous video, there were some other questions that came up. For example, what do we mean by speed of light anyway? And even if we can establish that the speed of light is the same in all directions, and would that necessarily mean that the speed of light is the same for all observers? So we've got a lot of things going on here, most of it pertaining to the last video. But what I want to, including the microwave oven, but what I want to focus on is um, two observers, one traveler and one stationary observer, and the famous experiment where if this person is turning on a flashlight inside of his spaceship that's moving at constant velocity, while inside the ship, would he see the light travel at the speed of light? Again, the conveniently rounded to 300,000 kilometers per second is what I use. And so that's question number one. Would that individual see? Now, according to the 1905 relativity, which is the entire crux of Einstein's 1905 paper, is basically to take Galileo's principle of relativity and incorporate light, so that including light, including electromagnetic propagation, the laws of physics would still be considered the same for something moving inertially as they would for something stationary. So Einstein's answer to that question is yes, I'm in the spaceship, I'm traveling at some percentage of the speed of light. I decide to turn on my flashlight. Would I see the flashlight traveling at the speed of light inside my moving ship? And according to 1905 relativity, the answer would be yes. Now, relativity from 1905 all the way up to the present day has been studied incredibly, and I think that 99% of all disciples of relativity would also say that an observer outside the ship, standing on a platform in outer space, wearing a space helmet hopefully, would also see that light go by that person at 300,000 kilometers per second. And so we would then consistently say that the speed of light is the same for all observers. It is after doing a careful analysis that started with that previous video and then just digging deeper and deeper and deeper, I actually found out some interesting things that I didn't have a complete handle on previous to my research for this last video with regard to light transmission before, during, and after. And it is my contention, based on that research, that inside the spaceship, the Einstein view of special theory of relativity that started in 1905, inside that spaceship, the Einstein view is, in my opinion, 100% correct. That if I'm traveling inside that spaceship and I turn on my flashlight up, down, front, back, and I measure the speed of light inside that ship, I'm not going to get any result any different than the 300,000 kilometers per second, and therefore, for that particular experiment, I would be able to confidently state that, at least at this point, it appears that the laws of physics inside this moving spaceship are the same as if that spaceship were stationary, and I wouldn't be able to use a flashlight in any way, shape, or form to tell the difference between inertial motion and being stationary. Okay? But it is also my contention that this stationary observer on this platform in outer space would see the light go by him at a speed faster than the speed of light. Okay? Why am I contending that? Well, before I get into that, I think what we have to do is first study some quote-unquote, in reality, textbook statements about light transmission. And again, we're going to look at some statements that are going to kind of walk us through the whole process of creating light. So, well, let me just get into these statements. The first statement, I'm going to read along here. Electromagnetic waves cover a wide range of frequencies. For example, radio waves are electromagnetic waves produced by oscillating currents in a radio tower's transmitting antenna. Light waves are a high-frequency form of electromagnetic radiation produced by oscillating electrons within atomic systems. Okay? So there's a reason why I'm presenting these exact quotes out of undergraduate physics textbooks. Okay? I'm going to go to another source here and extract this statement out. Visible light emitted by the glowing filament of a light bulb is one example of an electromagnetic wave. Unlike waves on a string or sound waves in a fluid, electromagnetic waves do not require a material medium. Okay? So with those two statements and everything else that the typical physics enthusiast learns about relativity and light, typically the story goes like this. Sometimes light is a wave, sometimes it's a particle. The speed of light is the same for all observers. It's a constant, regardless of whether you're stationary, whether you're in motion, whatever. The speed of light is the same for all observers. And we introduce the concept of time dilation so that there can be the rate at which time elapses, which will be a necessary adjustment so that the speed of light would be the same for all observers. And if we try to figure out the actual fine details of whether that would be true for these two individuals here, the traveler and the observer, and how that would be true from a mechanism standpoint, step by step, would the average person be able to actually put those steps together, or just throw their arms in the air and just say, well, the speed of light is the same in all directions. We have time dilation. Time dilation is a proven fact. It's definitely an existing phenomenon, which I've said 100 times before. I've never disputed. Time dilation is 100% real. And you're just kind of left with this acceptance based on this vague, opaque conglomeration of details, which then, hey, let's also throw in simultaneity and length contraction and stir them all up in a pot, and when it all comes out, we're just going to say that the speed of light is the same in all directions, and all of these other relativistic co-effects like time dilation and length contraction and all these things will fix it so that the speed of light is the same. And then if you want to dig deeper, you can get into a verification through Maxwell's equations about the electric fields and the magnetic fields and the propagation thereof. And then we just throw our arms in the air and just say, okay, I guess that's that. In my opinion, these two statements from these two textbooks really don't help one's cause in terms of figuring out what's happening on a deeper level. Okay, I'm going to read a third statement from this, which would be the second statement from the Sears and Zemansky's book. Actually, it's Young and Franklin, Sears and Zemansky's. And I put in electromagnetic, I added it there, that's why it's in parentheses. The electromagnetic wave front moves to the right in the positive x direction with a constant speed c. Thus, the E and B fields, which stands for E for electric field, B for magnetic field, travel to the right into previously field-free regions with a definite speed. Okay? So, now if we're trying to figure out the moment that light is created, what is happening, where is it happening, and just exactly how is it propagating? If we're familiar with the typical relativity story, we know that there is a big conformational test done that stated that there is no ether that the light travels in. The light travels in a vacuum, there is no ether, there is no medium, and it's the same, its velocity is the same for everyone. Again, to me that doesn't really clear things up in terms of a start to finish mechanism for beginning to end, before, during, and after the creation and propagation of that light wave. And so if we were to look at this model right here, the moment that this individual turns on the flashlight, then we would say, well then what's going on? At that moment of creation of that very first light wave, does it kind of deposit itself in free space, outer space, and then just start traveling on its own from that point to this person? In which case, then that would make the traveler and the ship and everything else on it that was moving at constant velocity separate or independent from this newly created light wave. So is that the situation? Or is the moment that that first light wave that's created at that point in space, in addition to traveling at the speed of light, is it also kind of plugging along with the velocity of the ship? If you try to pick one or the other, then you wind up with a conundrum, because then it's not going to work or balance for the other observer seeing everything at the speed of light. So it leaves you kind of like, well, maybe it's one, maybe it's the other. I'm not quite sure which it is. All I know is that it's the light travels in a vacuum. There's no medium, there's no ether, and it starts here and it finishes here if this person's going to measure the speed of light, and somehow when it goes from here to here, even on a moving ship, this person would measure it at the speed of light. Okay? Well, what exactly is a beam of light? Well, because in the outer space models where we're talking about turning on a flashlight, I just want to make a little side note here that there really is no such thing as a beam of light. When you're talking about a filament inside of a flashlight, or even an LED light, a higher efficiency LED light for that matter, what you've got is a whole bunch of separate, independent events that each in themselves produce a light wave. Now we could say particle, but we're going to stay with the wave model in this point. And when that filament full of atoms is energized, as a previous statement indicated, when the filament in that light in the flashlight is energized from some sort of electrical battery-powered power source, then each atom, one at a time, is getting excited, dropping to a lower level after it was initially excited, and it's giving off the energy equivalent in light that it experienced in terms of a loss when it dropped from a high energy to a low energy energy level. But again, the beam isn't one coherent object that's traveling as one individual entity. It's many, many, many light waves traveling independently, because each individual atom was kind of stimulated and then experienced an energy loss kind of at its own individual pace. Okay? So let's go back and take some more notes out of a textbook here and see if there's something further that we can figure out here. Consider a charge that is initially at rest, then is quickly accelerated for some short time interval, and then continues to move with a constant final velocity. The initial electric field lines originate at the initial position of the charge, but the field lines at some later time after the acceleration ceases must originate on the new position of the charge. The field lines cannot change from their initial configuration to their final configuration instantaneously. Rather, a disturbance must travel outward from the position of the charge and gradually change the field lines. The disturbance takes the form of a kink connecting the old and the new field lines. The speed of the disturbance is actually the speed of light. So what this is saying is, previous to any light being created, we know that all charges, whether it's a negative electron or a positive proton, we know that all charges contain an electric field that have field lines that travel out spherically in all directions. Those field lines are there before the light is created. Okay, so that's what we've got here. And conventionally, you will see the well, I've got this wrong actually, because if this is a negative charge, then the field lines should be arrows should be pointing inward. Okay, and then if it's a positive charge, the arrows are. It's just a convention thing. The positive charge, then there are field lines for both, but there's a directionality when you're trying to figure out whether you're going to have an attractive force or a repulsive force between two charged objects, and it obviously makes a difference between whether you have like charges that would repel or different charges that would attract. So the field lines conventionally would be drawn different. So the arrows are pointing out for the positive charge, and the arrows should be pointing in for the negative charge. But so anyway, so we have existing electric field lines around all the charges in the filament of the flashlight. Okay, and what's happening is, according to this statement, the initial electric field lines originate at the initial position of the charge, but the field lines at some later time after the acceleration ceases must originate on the new position of the charge. So an adjustment is made. Previous to this individual turning on the flashlight, the individual, the flashlight, the ship, and everything in it, we're all traveling as a unit inertially at some constant velocity. Okay. But all of the atoms in the filament are still have charges in them. There's still electrons in those atoms. There's still protons in those atoms before that light has been turned on. So all the atoms in the filament and all the subatomic particles of the atoms in the filament all have electric fields emanating from them, and we're illustrating that with electric field lines that spread out in all directions. Well, those electric field lines, along with those charges, are all traveling as a unit as well. Okay, so that's something to keep in mind. But when something happens, and for example, if the word acceleration would make more sense if we were talking about the generation of radio wave signals, because it would be a constant acceleration, deceleration of charges, which would be creating waves. And it would be perfectly timed so that as wave number 1 comes to an end, wave number 2 just starts to pick up or engage. So what it looks like is you've got a train of continuous waves that are basically propagating at a particular frequency, with the wavelength being the same for every one of them in that very long train of waves that would then be picked up by some antenna somewhere else, by somebody listening to the radio. So, in terms of the word acceleration, that is more intuitive. I suppose we could use the word acceleration when an electron falls from a high energy position to a low energy position, which thus would also create a wave too, similar but yet at a different frequency than the radio waves. But there still seems to be some issue as to whether the drop from a high position to a low position, which actually creates the light wave to begin with, there's still some discussion as to, hey, is that an instantaneous process, or is some tiny period of time going by during that actual drop there? So I suppose we can keep using the word acceleration for the example where we would be creating visible light from electron falling from one position to another. It isn't as intuitive as the radio wave example, but we'll just keep using it anyway. Okay. Going to stay with the same textbook, different statement. The traveling kink is a single wave pulse, analogous to the single wave pulse we might produce on a stretched string by flicking its end just once. If we want to produce a periodic electromagnetic wave, we have to accelerate the charge back and forth periodically, like I had mentioned with the radio wave earlier, and thereby generate a succession of kinks in the field lines. This picture of an electromagnetic wave as a succession of kinks in the field lines explains how such waves are able to travel in a vacuum. The electromagnetic wave does not really travel in a vacuum. I'm going to read that line again. Please do not adjust your sets. The electromagnetic wave does not really travel in a vacuum. It travels on the field lines of the charge. That is, it travels in the electric field of the charge. The space surrounding the charge is not really a vacuum. The space is filled with the electric field of the charge. And this electric field is the medium in which the electromagnetic wave propagates. Isn't that terrific? That clears up a lot. So if we're talking about radio waves, we could have something like this, depending on the frequency, where it would just be this continuous train or continuous stream of waves, and as one wavelength comes to an end, the other one seamlessly starts wave number 2 and then wave number 3 and so on for as long as they're generating radio signals. So it's appears to be one long train, whether it's a higher frequency or lower frequency. But with the filament of a flashlight, again, it's a more incoherent situation, because there's just this energy from the battery and the flashlight, electrical energy shooting to the filament, which is energizing the filament. The atoms in the filament are getting excited, and they are haphazardly, from accepting that electrical energy, promoting their electrons to a higher energy, and then falling to a lower energy, thus giving off light. But they're all kind of doing it independently of one another. So again, it helps to know that if we're talking about a flashlight example, as opposed to something like a radio wave or maybe even a laser, which would be, if properly designed, would be more coherent and would be more resembling the radio wave model than the haphazard, incoherent production of individual waves here. It just helps to understand the difference between the two if you're going to be doing thought experiments and using models like that. Okay. So, what can we say about light? And so this would be back to my statements now. The properly timed continuous oscillation of charge to produce radio waves can provide a continuous stream of electromagnetic waves where one begins right where the previous one ends. Properly designed lasers can produce similar waves. Light, however, from the sun, a flashlight, light bulb, or candle will generate trillions of independently traveling wave fronts, sort of, through space, air, or water as the electrons of each light-producing atom shift and create a kink in their already existing electric fields. I say sort of because you can get some, superimposed wave effect if, like, say, for example, if two atoms at different spots of the filament just happen to go up and come back down at precisely the same time, or near enough to the same time, you could actually produce a superposition effect, or where that you'd have a single wave that would actually be higher in amplitude from those two events contributing to the same cause, so to speak. But that aside, I mean, you have again a whole bunch of just individual events just cranking out one after another, and by the way, at different frequencies all over the place too, including infrared, and the typical flashlights with a filament is generating all kinds of heat, again, as opposed to an LED, which is more efficiently designed to have electrons fall from a higher to a lower energy position within the visible light spectrum. So that's why you get more light and less heat and less energy wasted with an LED. So, in short, each light-producing atom was already equipped with its own personal ether in the form of the electric field lines extending outward. As the shifting electrons in these atoms facilitate the production of light waves, they do so by shifting relative to the position of their own field lines, and the wave is a propagating adjustment, a kink or a ripple if you like, of the field to the electron's new position. So if we look at these two figures in this particular slide, we would have a charge that would have a bunch of field lines emanating out from it in all directions previous to the acceleration or light creating event that charge would be experiencing. And then on the right side, we would basically have a wave already in progress based on that charge doing something, accelerating or dropping from high to lower energy level, where the field lines everywhere spreading out to infinity would not be able to instantaneously adjust to that charge's new position based on the acceleration or that light producing event that it had just experienced. So as you can see in the second figure, we'll see the charge as that black dot in the almost center of that second figure, that second box there. And what you've got is the two circles, and then outside of the two circles. Well, inside the two circles, the adjustment has already been made, because that makes sense, because those field sections of the field lines are the closest to the charge, so they would have been the first to adjust to that charge's new situation. At the far reaches, up to the end of the square figure there, we would have the field lines that have not yet gotten the signal that something has happened with that charge. So those field lines are still in the old location based on the previous situation of that charge before it experienced that light-producing event. And the two circles in the middle is what's separating the already adjusted field lines to the yet-to-be adjusted field lines. And those two circles are the location where that electromagnetic wave exists and is propagating at that very second. Okay? So hopefully this will provide enough detail so that you can see from a mechanism standpoint the before, the during, and the after of the single event of the creation of a light wave. Okay? Now, in fairness to the Sears and Zemansky's text, they also have something similar. I'll read that too. Field lines are not material objects, but you may nonetheless find it helpful to think of them as behaving somewhat like strings that extend from the point charge off to infinity. Oscillating the charge up and down makes waves that propagate outward from the charge along these strings. So again, Sears and Zemansky this is the statement that would be synonymous with what the Ohanian statements have said. But if you were to take all of the statements from Sears and Zemansky in their entirety, you still might be a little bit confused, because in a previous Sears and Zemansky statement, they talk about, well, let me go back and quote them correctly here. They say the electromagnetic wave front moves to the right in the positive x direction with a constant speed c. The E and B fields travel to the right into previously field-free regions with a definite speed. So, in a sense, that's correct, because if you're looking at the way that the fields look and the magnitude, the strength of those electric and magnetic fields are experiencing at the location of that wavefront, then in a sense that's correct, because in the future where that wave hasn't traveled yet, that particular form of wave, being the electromagnetic, the electric field and the magnetic field experiencing those changes there, that would not have propagated forward yet. So if that's what you're considering a previously field-free region, then I suppose that would be correct, but it's not field-free in the sense that what is responsible for these fields being able to first be produced and to travel to begin with. It would be the existing electric field lines emanating from the charges involved in producing the light to begin with. And those field lines were already there, and if these charges didn't have electric fields around them, they wouldn't be charges, and light would not be produced. So the existence of those fields emanating from each one of those charges before the light is even produced is 100% essential. It's necessary for the light to even exist and propagate. So again, I would much rather reread the statement, the electromagnetic wave does not really travel in a vacuum, it travels on the field lines of the charge, okay? So I'm a bigger fan of how Ohanian had phrased that, but again, in fairness to Sears and Zemansky, in this particular section, they are also stating what's the statement synonymous with the theme that Ohanian is making. So make no mistake about it, we do need those field lines to exist, because that is the medium or the personal ether that each one of those charges are carrying around previous to making that light. Okay? All right. So now let's revisit this. Okay? So it is my contention that that Einstein and all that subscribed to the 1905 version of special theory of relativity is 100% correct. It is my contention that Einstein is 100% correct, because when you're in this moving ship and you turn on your flashlight and you generate a light wave, or 1,000 light waves, well, let's just say a one individual light wave, and it could be up, could be down, could be to the forward direction of the ship, or could be shining backward. Then what that individual is going to see, if they had the capability of measuring that, is that light wave would be traveling along the field lines at the speed of light. But the field lines that were part of the charges were all moving inertially together as a unit. The individual, the ship, the flashlight, the atoms in the flashlight, and the field lines coming out of every single charge that's in those atoms in that filament. So previous to flipping on the light, everything, including the field lines, were all traveling with a constant velocity as a unit. Now you turn on the flashlight and you create a ripple or a kink in those pre-existing field lines, and that kink or ripple will travel along those field lines at the speed of light. So since everything's traveling as a unit, then that individual, if they were capable, would measure, regardless of whether they were pointing the flashlight in the forward direction or in the backward direction, opposite of what the direction that the ship is going. It wouldn't matter. That individual would measure light waves coming out in every direction at exactly the speed of light. And in that particular case, they could state, if that was their way of determining it, they would say, at least for that behavior of light, that the laws of physics would be the same for this inertially moving spaceship as they would be as if the spaceship were stationary. I'm in 100% agreement with that. On the other hand, we have this observer here who, before that flashlight is even turned on, if they had special glasses that could see the field lines of these charges, they would see the field lines of the filaments, which are extending outward, presumably forever. They would see the field lines already in motion at the inertial, at the constant velocity that this inertially moving ship is traveling this way. And as those field lines are going by, this person turns on their flashlight, and that flashlight sends out a kink or a pulse along those existing field lines that were already moving with some velocity, but the pulse or the kink itself is moving at the speed of light along the field lines. So this individual, I contest, would actually see the speed of light as faster than 300,000 kilometers per second. And in my opinion, that would be the explanation for the generally accepted relativistic Doppler effect. And honestly, whether you measured a relativistic Doppler effect or a non-relativistic Doppler effect, you're going to get in this situation you're going to get a blue shifting. All right. Now, if you need a primer on the relativistic Doppler effect with light, Alan Guth and the MIT YouTube channel does a really good, I'd say like an hour and 15-minute long lecture on the relativistic Doppler effect. And to supplement that, if you want to fill in some of the simple blanks, you can even go to the Wikipedia page and look at the, mathematically they even have like a little box where they can show you the difference in the extent of the blue shifting, whether it's a relativistic Doppler effect or non-relativistic Doppler effect. The point is we could argue that all day long, but whether we're taking all of the relativistic co-effects into consideration or not, this person would still experience a blue shifting of light. And the only way that they could experience a blue shifting of light would be if the front of the wave, the amount of time that went by from them experiencing the front of the wave and the trailing end of the wave happened more quickly, and so therefore they would see that as a blue shifted light which would have a shorter wavelength compared to something that would be, what it was originally. Okay, kind of tough to take, but the facts are the facts, right? So, because of the Doppler effect, observer B will see the light moving faster than the speed of light. And by the way, if the ship was already by the observer and the person was shining the flashlight in the backward direction, then in terms of Doppler effect, that light would be redshifted. And that's, again, that's a known fact. But based on everything we now know about the personal ether that each one of these charges are carrying around with them before, during, and after the creation of that single event of creating a light wave, we know that the reason for the person experiencing the red shift that is behind the ship and is getting the light shining in the backward direction is that the light would be traveling past them at slower than the speed of light, and that would be the reason for that. So, if you'd like to comment, have at it. Why not?